Hello everyone. Today I'm going to be explaining the technique nodal analysis, and I'm actually going to be teaching the fastest way to write the nodal equations for nodal analysis. So let's get started. So what is nodal analysis? Well, nodal analysis is a circuit technique that uses KCL and Ohm's law to calculate node voltages. So the best way I could explain this is through a circuit example, and I'm going to be teaching you how to do this method step by step. So looking at this example, we have all our resistors for this example is going to be 2 ohms, and my current source IA is 10 amps, and my current source IB is 6 amps. And so the first step is to label all your nodes, and I've already done that here. But if you don't know what a node is, then you cannot proceed for a nodal analysis because it's literally in the name, nodal analysis, and you won't be able to understand what's going on if you don't know what a node is. And I'm going to briefly explain it. So a node is anything between two or more elements. So I have my element R1 here, an element here, IA, and my element here, R2, and what is between them, or what is the connection between them? This node. And I'm calling this node VA. So now that you know what a node is, hopefully, then you can proceed. So I'm going to be labeling this node as A, this node as B, and this node as C. And I'm going to be grounding my node D down here as 0 volts. And you could pick the ground to be pretty much anywhere. I'm picking the bottom for now, but in certain cases, you could actually pick the ground anywhere, and sometimes grounding the bottom isn't always the best case. You'll see that in later videos, and I'll be explaining that later. But for now, let's move on. So our next step is to identify our knowns and unknowns. So what do we know? We know that VD is 0 volts. And we're not given any information about VA, VB, or VC, but we could write nodal equations. So I'm going to be writing question marks for now because we don't know what these voltages are. So looking at this, I have 3 unknowns. And since I have 3 unknowns, I'm going to need 3 nodal equations. Exactly, and this will always apply to every circuit. However many unknowns you have is how many nodal equations you'll need. Now my next step is to actually write the nodal equations. So I'm going to start in the order from A, B, C, and I'm going to be writing my nodal equation in the order of A, B, C to make it look nicer and easier to enter in my matrix. So I'm going to be writing KCL at VA. And the trick here is to take this, the node you're looking at, the node you're writing the equation for at, as positive. So my VA will be positive, and any other neighboring nodes will be negative. So my neighboring nodes that are connected to VA are VB. So I'm just going to write over here neighboring nodes. You don't have to, but VB, VC are going to be negative. And I'm not actually going to be writing anything at all for VD because it's 0. We don't need to include that in our equation. Anything that's multiplied by 0 is 0. So the neighboring nodes for this are VB and VC, and those are going to be negative. So I'm going to be writing VA, and I'm going to look at any resistors that are attached to VA, and I'm going to multiply that by VA. So VA multiplied by R1, since it's attached, and multiplied by R2. And it's going to be 1 over R1 plus 1 over R2. And you're probably wondering why. Well, we're doing KCL. We need currents. So looking at Ohm's law, I is equal to V over R. So we can't do V times R because that is not Ohm's law. We need Ohm's law. So V over R. That's why I'm doing 1 over R, which is technically called conductance. And now I'm going to be subtracting that from any neighboring nodes. So minus VB, and I'm going to look at any resistors that are connected to VB and VA, and there is no resistor. It's actually a current source. So I'm going to write zero resistors or conductances. And if you guys don't know what conductance is, it's just G. The symbol for it is G. And that is equal to 1 over R. And it's just a better way to say 1 over R. It's faster. So 0 conductances or resistors attached to VB and VA, and then minus VC. And I'm going to be looking at any resistors connected to VA or VC. Yeah, there is actually. There is R1. So that's going to be included in my equation. So minus VC and 1 over R1. And that equals to, and now here's where my current source is. I'm going to have to be looking at the current sources. So are there any current sources leaving or exiting the node VA? Well, there is actually. There's IA. And what is IA doing at this node? It's leaving this node. It's actually leaving. The arrow is pointing away. So I'm going to be writing minus IA, and IA is just 10 amps. And that's our first equation. And you'll notice that I didn't include VD. Why? I explained it before. It's 0 volts, so anything multiplied by it is 0. So now that I've explained the first equation, try to write the second equation without looking at my answer, and then play the video. Okay, so now I'm going to be doing KCL at VB, just follow the order, and my VB is going to be positive, and my neighboring nodes are VA and VC and VD, but I'm not going to be writing VD, so VA and VC are my neighboring nodes, and I'm going to be writing them as negative. And this is the trick right here. This is much faster than the traditional method, and there's less chance for mistakes. So I'm going to be writing from A, B to C in order. So VA, and I'm going to be looking at VA. Are there any resistors connected to VA and VB? No, there's not. There are 0 resistors, so 0. And then plus VB, that is going to be positive, and multiplied by any resistors connected. Well, I have 2 resistors connected, R3 and R4. So that's going to be included. So 1 over R3 because of Ohm's law, plus 1 over R4, and then minus VC. And are there any resistors connected to VB and VC? Well, yeah, there is. There's R4. So there's 1 over R4. And that's equal to the currents going in or out of the node. So IA is actually pointing into VB, and IB is leaving the node. So I'm going to be writing 10 minus 6, because IA is entering, and then IB is leaving, so 10 minus 6. And that's my equation 2. Now for my final equation, I'm going to be doing KCL at VC. And I'm going to be looking at my neighboring nodes. So, neighboring nodes. Are VA and BB. So I have VA and BB as my neighboring nodes, and I'm going to put a little space here because it's getting kind of tight to write all this. And what am I going to be doing? Well, for the signs, I've explained this before. VC is going to be positive. The KCL that you're doing the node at will always be positive. And then all the other voltages, the neighboring voltages, are going to be negative. I like to write this in blue. So let's do it. So I'm going to start from left to right, VA. So VA, I want to include my whole circuit. So VA is negative minus VA. And are there any resistors that are connected to VA and VC? Well, yeah, we do. We have R1. So minus 1 over R1. And then, are there any resistors connected to VB and VC? Well, yes, there's R4. So minus VB divided by 1 over R4, and then plus VC and multiplied by all the resistors that are connected. So 1 over R1 plus 1 over R2 plus 1 over not 1 over R2, 1 over R4 and plus 1 over R5. And I'm just going to write that again, but neatly, because there wasn't much space. 1 over R1 plus 1 over R4 plus 1 over R5. Yep, and that is equal to any current sources going in or out of the node. And current sources specifically, well, there is no current sources going in or out. So I'm going to write 0. And that's my equation 3. So those are all the nodal equations. Now I could actually write these equations into a matrix and solve the reduced row echelon form of these equations, and I could get my node voltages. So I'm going to quickly write down the matrix, and you could fast forward, but I'm just going to be showing this just in case people want to see. So for my VA, also, if you guys remember, my resistor values are just 2 ohms, so I'm just going to be writing, so my first is, well, this is the matrix that I'm going to be writing. So this is my matrix, and these are my voltages, VA, VB, VC, and this was minus 10, and I'm going to write 4, just do the subtraction, and then 0. And then I'm going to be writing, so everything is equal to 2. All the resistors are equal to 2. So I have 1 here, 1 over 2 plus 1 over 2 is 1. And then I have 0 here, and then I have minus 1 over 2, and then I have 0 again, and then I have 1 again, and I have minus 1 over 2. Let me just double check. Yep, minus 1 over 2. And then I have minus 1 over 2 again, minus 1 over 2 again, and 1 over 2 plus 1 over 2 plus 1 over 2 is 3 over 2. So this is my matrix. And now if I actually solve the reduced row echelon form of this, then I could get my answer. And if you guys don't know how matrix multiplication works, well, this VA is gonna go all the way here and multiply by this whole column, and this VB is gonna go all over this column and be multiplied out, and this VC is gonna be multiplied all over here. And once you solve this, you'll get your reduced row echelon form. So after putting it into my matrix calculator, I am getting VA, VB, BC, and there's like ones obviously in front of this. 0, 0, 0, 0. Sorry, I put too many zeros. 0, 0, 0, 0, and I should put the cylinder. And I'm getting minus 1.5, 2.5, and minus 3, and these are all in volts. And these units are all in volts, and that's how you actually get the node voltages. And you can do the matrix calculator by hand, but I did it with a calculator because it's much faster, and you're obviously going to be allowed to use your calculator for the test. So that's it for this video. I know it did take a while for me to explain it, but trust me, once you get the hang of this method, it is the fastest way to do the nodal equations. And if I wasn't explaining the method to you guys, I could have wrote these 3 equations in, I kid you not, less than a minute. So I hope you enjoyed. And in my next video, I'm probably going to be going over other types of cases for nodal analysis. And I'm going to be moving a little faster. In this video, I want to go really slow so I can explain each and every step of the nodal analysis process. So I hope you enjoyed.